Thank you very much, Dr. Z. Pleasure to be back for the perennial talk in the experimental math seminar. And okay, so the title has been a little bit abbreviated here, so I didn't want to go overboard. And so this, of course, mentions already in entropy with sign and complex measures. So far as I know, nothing like that exists, right? And well, it exists in a publication of mine. But let me give you a slow introduction, recalling first of all what entropy really originally meant, and so on. So it all starts with this man in 1865, right? So that's in a path-breaking paper. He invents the word entropy. It actually is an artificial word, so the N somehow means inside. The trope comes from the Greek from transformation, turning, and he wanted something that sounds similar to energy, so he called it entropy at the end. So, and it referred to an interior transformation that he pictured. He was an atomist, mind you, right? This is 1865. Thermodynamics is a continuum description of matter, or part of the continuum description of matter, and people had found ways to measure the energy content of objects, of bodies, of fluids, and based on the idea that certain transformations should take place from a higher to a lower energy state, they expected certain things to happen and they didn't happen. And what Clausius realized was that related to the second law of thermodynamics that had been already discovered by Carnot with his cycles, that there must be some interior transformation going on of the atomic structures of the bodies, and that will eat up some of the energies, right? And so if there's a penalty to be paid, and so that's what he basically was proposing.
So entropy was coined by Clausius or by Carnot?
No, by him. The second law of thermodynamics goes back to Carnot and earlier people at the same time, roughly as Carnot. That's what I mean.
But he did not use the word entropy?
No, that's to my best knowledge, he introduced the word entropy in that 1865 paper. And but of course, as I said, Carnot cycles, he refers to things you do in the laboratory, right? But he was thinking big. So at the end of the paper, you will find the following two statements. The energy of the world remains constant. The entropy of the world tends towards its maximum. So these are the last two sentences in that paper. So he applied what he thought had discovered. So he formulated basically the second law of thermodynamics using the concept of entropy. Before it was formulated in different ways. All right, good. So much for Clausius. Soon after, Clausius introduced the concept but didn't write a formula that connects the atomic structures that he supposed were there with what he called the entropy. That was done by Boltzmann in 1872. And in particular in his kinetic theory of gas. There's also Maxwell made contributions, of course, earlier than Boltzmann already. And he introduced now what he called the H-functional. And I have to explain that a little bit. So this is Boltzmann's H-functional. So you should think of this here as S for space point. Okay. So this is actually this is a scalar function, actually a normalized scalar function for me here, that is non-negative, integrates to 1, right? And this is actually the cotangent bundle of physical space. So, and where is the atomism? Well, it's, if the p's were not there, then this would be a continuum description of matter. But he said, no, at each space point, right, of course, you look into the neighborhood, the small local neighborhood, there are many, many atoms, and their velocities and therefore momenta have a certain distribution, and that's what needs to be taken into account. What is important here is that, nevertheless, this is a continuum approximation. This f here, that's f ln f, is the expression here, but f is a continuum approximation to an empirical density on the cotangent bundle. Even though you normalize it, right, and formally, technically, it would be a probability density, but there's nothing really probabilistic in that beast here. And well, the entropy is then the negative of this. N is the number of particles in it, and Kb is the Boltzmann constant that was introduced by Max Planck. Boltzmann never bothered to introduce that beast. Alright, so here is then something much more subtle. I mean, that was already not so bad what Boltzmann did there with his Boltzmann H-functional, but already starting in the 1860s, he actually proposed the following, that in thermal equilibrium, so now you take a system of n atoms in a domain. I'm using a little bit notation. V here stands both for the domain and for the volume of the domain, right? So I didn't want to become too petty here. Delta is the Dirac delta measure, right? H is defined here. That is what physicists call the Hamilton function. P again, pk is the momentum of kth particle. All particles have same mass for me here, and so this is the kinetic energy, and this is the sum of the pairwise interactions. For instance, Boltzmann was contemplating repulsive interactions, like 1 over r to the 4. Actually, they are called Maxwell molecules. A molecule was referring not to what the chemists call molecules nowadays, but particles, atoms, right? And and Boltzmann contemplated that too. But if you ask what the physicists are doing, for instance, the noble gases, neon, argon, krypton, xenon, argon, helium is too light, so that is a little bit out of this, are very efficiently described by a classical interaction, Hamiltonian, with such a so-called Lennard-Jones interaction function. That's a positive constant, and R has to be empirically matched to some data for either neon or argon, so that means each of these elements has its own R and A. But that gives a very accurate description of the behavior of those noble gases for a large range of temperatures and densities. Of course, if you cool them down to near absolute zero, and then quantum physics becomes important. Okay, so now this is what Boltzmann wrote down, basically. Well, he didn't write it down exactly like this, but it's in his writings. What is this? So you integrate now, not over the cotangent bundle of physical space, but you integrate over the cotangent bundle of configuration space of labeled positions of n particles. Take the log, take minus k Boltzmann. Again, he didn't have k Boltzmann there. And he said that's the entropy. Well, wow, what beast is that? Well, what he realized is that by a law of large number type argument, that almost all the points in the cotangent bundle of configuration space, the individual point contains all information of all the positions and the momenta at a snapshot in time of a, say, gas. And he realized that almost all the points macroscopically have the same empirical statistics. If you bin that into blocks of 3 for the positions, blocks of 3 for the velocities or momenta, on the velocity side you get the Maxwell distribution with very high degree of approximation, and on the position side it's more or less uniform with some pairwise correlations. Almost all points look the same. In other words, macroscopically speaking, they all must have the same entropy, so therefore the size of the energy surface in the cotangent bundle, also here the delta takes care of that, is basically a measure of the entropy. That was his great insight. And therefore, he doesn't formulate it as theorem and proof like we would do nowadays, but this can be completely rigorously shown. But he did it first for the perfect gas, means no interaction at all. And here's the connection with his H functional. Namely, if you take that expression that I just wrote, this 6n-dimensional integral with a delta measure, divide by n, scale the energy proportional to n, scale the volume to be proportional to n also, and then let n go to infinity. 1 over n of this beast goes to the max of this with respect to f, where f is non-negative, integrates to 1, and the kinetic energy is a fixed per particle. Kinetic energy per particle is some little epsilon here. So that makes the connection. That's the maximum entropy principle for the thermal equilibrium state of a perfect gas, connected with this H1. So basically, it's like a law of large number consequence. So he also put some thoughts into interactions, and of course, nowadays means, in particular in the 60s, this started, 1960s, 100 years really later, that mathematical physicists got their hands on this with non-trivial views. Dermot Well, one of our distinguished visitors every year, he is one of the masters here, so is Joe Leibowitz. They make major contributions in making this story rigorous when you use non-trivial. And the most famous of them all is this formula, also not written by Boltzmann, but by Max Planck again. Right? And so when you look closely, exactly this is here. They put a dot where I put normally a k dot b, so I left b out here. And so that is the tombstone of Boltzmann and some relatives of Boltzmann, and he looks really like, so it's funny that these portraits they somehow go overboard a little bit. And
so this is famous formula?
That's the
it's
formula.
Not due to Boltzmann?
In spirit it's in there. He didn't write that, no.
Oh, in this form it's due to Planck.
This is Planck. Planck wrote it
So
down.
it was implicit.
And basically what Planck here means, what is W? W Planck used for the German Wahrscheinlichkeit, probability, right? So it's entropy is basically proportional to the log of the probability, means the relative size of the accessible phase space. And what? Well, you take a Markov state, no, it doesn't need to be equilibrium state, you ask what is the size in the cotangent bundle of configuration space that corresponds to this Markov state. Right? And the equilibrium state has by far the vast size. Right? And so speaking in these relative sizes defines what you mean by W. And of course for the equilibrium state it is basically all. Right? And that was the previous formula. Whoops, I went in the wrong direction. No, where I'm going here. Something is... No, something is... This one, sorry. Right? Again, here's now negative. Okay, put it in. It's ln 1 over this integral. So this is basically the W then. So now we've got a sneak preview already of what's coming. We're pushing the wrong buttons here. So, okay. Next. Planck did these things around 1900, so also around 1900 is Gibbs. Josiah Willard Gibbs. So he writes his book on the principles of statistical mechanics, and so he introduces an ensemble entropy that looks very similar to Boltzmann's H function, so already a minus sign there, now again over the cotangent bundle, not over of configuration space, not cotangent bundle of physical space. And many physicists thought, oh, this must be much better because there's much more information. Look, we have n particles, all the particle position, but this, of course, this f, if you say it's non-negative and integrates to 1, is now literally a probability density on the space of all possible systems having n positions and particles and things that have all momenta also. So it's an ensemble. So this is an ensemble entropy, while Boltzmann's formula was the entropy of a Markov state of an individual system. That's the big difference. Right? Okay, but it's a very useful thing. And well, so Gibbs showed that there's also a maximum entropy principle here, that if you maximize his entropy functional over all possible f's, non-negative, integrating to 1, so it's probability densities, with this constraint that the expected value of your Hamilton function that I had shown earlier is a fixed energy E, then you can evaluate what comes out is this, that's this value E divided by T. T is a temperature, that's a Lagrange parameter actually that you need to satisfy this constraint here. It shows up also there again. And so this is his formula for the maximum. And so quite some effort in mathematical physics went into studying such objects here. The double integrals are called partition functions. in the physics literature. Remember that H was a sum of squares of P plus a double sum of pair interactions. So with the exponential here that factors gives you basically n times the Maxwellian, the Gaussian, which can be integrated. So all the hard work really gets into these Q3n dimensional integrals with the interactions to control what happens there, and all the interesting things like phase transitions, transition from liquid to gas, should actually be in that thing. And believe it or not, nobody has today rigorously shown that liquid and vapor have a real phase transition mathematically. So it's only shown with certain approximations, but not with these models. Nobody has managed to pull that off yet.
Did you try?
Yeah. But if I cannot do it, who can? Just kidding. But I know it's very hard. Well, there are all kinds. That was history. So now, of course, the history goes on somewhat, but I chip in probability, quantum physics, the information age, because there's a proliferation of entropies, right? For instance, Mr. von Neumann, of course, made major contributions to the foundations of mathematical formulation of quantum mechanics, introduced the von Neumann entropy. This is a trace, always now what physicists call a density matrix. It's a trace class matrix, and the trace is 1, so it plays the analog role of a probability density function in classical physics here. And the trace plays the role of integrating what you have seen before. So that is von Neumann's entropy. Then comes Shannon's information entropy, the Kullback-Leibler divergence, or also called relative entropy. Notice there's a different sign here. It's not a typo, that's how it is defined. And normally for Kullback and Leibler, both P and Q are probability measures, but one can generalize this so that P is a probability measure, but Q is just a measure. Right? And already in a nutshell, this is what my talk is about, but it's not a measure. I mean, what's coming up. That's fine. By the way, there is also a very interesting story connected to this, that Shannon introduced this information measure and talked with von Neumann, explained it. Von Neumann was in Princeton at the time, and asked him, what shall I call it? And von Neumann said, why don't you call it entropy? Nobody understands what is entropy, so you have an advantage in any discussion. And so he followed that advice, and it became the Shannon entropy. So now I will, from now on, concentrate more on this beast here. So, mathematical physics. Fast forward, says up there, Onsagos vortex ensembles and differential geometry. So here's a theorem, and so that when you look back at the definition I just showed you for the books, here for the Kullback-Leibler entropy, X is some measure space. Now that gets much more general here now, and P and Q were measures on that P a probability measure. So therefore, why don't we do this? Let X be now the n-fold Cartesian product of R2. So we take n points with positions in R2, the Euclidean space. And our so-called a priori measure, dq, is what you see up there in the first line. So the e to negative h over n you saw from Mr. Gibbs already. There was this integral e to negative h, and there's a 1 over t, I skipped that here. And but there's also a factor now, a product over all little k from 1 to n, that means over all particle position of some function capital K of qk dqk, and let's say it's a Schwarz function, goes rapidly to 0 in all derivatives, and